Okay, so this is going to be quite a detailed video that I'm going to produce just to discuss the 5 main reaction types that you need to know for level 2 and level 3 chemistry. There is a 6th type of reaction, which is acid-base hydrolysis, and I will discuss that in a separate video because that comes more into play only for level 3, and you could make an entire video just to explain it. So for now, I'm just going to cover these 5 reaction types. So R stands for redox reaction, A stands for addition, and C stands for condensation, E stands for elimination, and S stands for substitution. So that acronym RACES I just used to help students remember, and myself, the 5 types of reaction. So you can just think of 2 people running a race, and that is your little visual for that acronym. So what the approach is going to be is that I'm going to go through each of the 5 types of reaction. I'll give you a brief, simple definition of what each reaction type involves, and then we look at a specific example of a compound undergoing the reaction, and throw in any relevant chemistry where possible. And just to give you an overview of the approach that I'm going to take, I'm going to start off, despite the acronym starting with redox reactions, it's more logical if I number it as follows. So I'm going to start with addition reactions and alkenes because that was the main focus in level 2. And because there are 6 addition reactions on alkenes, that opens up so many other possibilities with your organic synthesis. So that's most important to start with that. So after addition on an alkene, I'm going to look at elimination. So to go back from something that you've added to form an alkene. So elimination will be number 2. Number 3 will be substitution, specifically nucleophilic substitution. And then number 4 will be redox reactions, and then that will bring us over to the side of the poster where we can talk about condensation reactions. So if you take a look at how that's going to flow on the flow chart, I just have the level 2 flow chart here. We maximize that so you can see it a bit better. Now, I just see if I can. Okay, so here's my level 2 flow chart opened in PDF Annotator. So if I show you the approach, number 1 I said was going to be alkenes, so we focus on addition reactions of alkenes, and I'm just going to take the addition reaction where you form, let me get the appropriate color here now, where you form an alcohol by addition of H2O, because that's an example of asymmetric addition. So I'm going to follow this path here, and then we'll go back to alkenes from alkanes. That will be our elimination discussion. The third thing I said we were going to cover then were substitution reactions. So the substitution of bromine on alkanes is relatively simple, and most students pick that up easily in level 2. So I'll decide to look at substitution on a tertiary alcohol instead, using PCl3, PCl5, SOCl2, or Lucas reagent, because it's a bit more detail and teaching that can be done there. So that will be our substitution example. So we look at that. So addition will be number 1, elimination will be number 2, substitution will be number 3, and then redox, we look at redox reactions of alcohols, specifically primary and secondary. For level 2, you don't need to know about oxidation of secondary alcohols, but you might as well pick it up now. And then for the final type of reaction, the condensation, I'll take a look at the formation of esters from carboxylic acids, and I'll also take a look at the formation of esters from acyl chlorides, which is specifically a level 3 concept again for those level 2 students who are watching this right now. So that's going to be the flow. Number 1, alkenes, addition reactions. Number 2, elimination on an alcohol back to an alkene. Number 3, substitution on tertiary alcohol to form haloalkanes. Number 4, oxidation of alcohols. Number 5, the condensation reactions to form esters. So we go back to our sheet here where we can do a bit of writing. So the first thing I want to talk about then is addition reactions. So number 1, addition reactions. So an addition reaction, simple definition for it is that it involves a double bond being attacked or broken. So a double bond is broken, and atoms are added into the molecule. Atoms are added into the molecule. Alright, so addition reactions are specific typically to alkenes, though as somebody pointed out in the lesson this week, of course, you can have addition on alkynes as well, which is a triple bonded carbon. And this was the main focus for your organic synthesis with level 2, and it's still necessary to be aware of it for level 3. Okay, so that's your definition. Because there are so many addition reactions, I also use this acronym with students to help them remember. So I use this 4-HOP acronym. And the 4 infers that there are 4 addition reactions that begin with the letter H. That's why the 4 is there. So one of the possibilities is hydration, which, as the name suggests, is addition of water, H2O, to an alkene. You have halogenation. Halogenation involves the addition of a halogen atom, which are group 7 elements such as fluorine, chlorine, iodine, or bromine. Specific focus on chlorine in level 3. You have hydrogenation reaction, which is addition of hydrogen, and that's how you return to an alkane from an alkene. And then finally you have hydrohalogenation, which I'm going to focus on in this specific example. Hydrohalogenation involves the addition of HBr or HCl, for example. So the hydro part refers to the hydrogen, and the halogen back to the halogen atom, group 7 elements. So the specific example that I want to look at involves asymmetric addition, because this brings in Markovnikov's rule. So if we're going to look at asymmetric addition for a second, asymmetric. So asymmetric addition. So a nice little link here to structure and bonding. If you remember, an asymmetric molecule is a polar molecule because the polar bonds don't cancel. So HCl is a great example. The molecule is visibly asymmetric because you have a small hydrogen atom and a large chlorine atom involved, and the molecule is polar overall because it's asymmetric. So this is an asymmetric molecule. Another good example of an asymmetric molecule would be H2O. Again, H2O has polar bonds in it. The polar bonds don't cancel, so it's asymmetric arrangement of the polar bonds, and therefore this molecule is polar or asymmetric. Also, in terms of visualization, OH breaks down, or water breaks down into H plus and OH minus ions. We talked about this in lesson during the week, which is where the asymmetric split comes in as well. So in any case, HCl and H2O are good examples of asymmetric molecules, and they're polar. Br2, for example, is symmetrical, same atom either side, so that's symmetrical, and non-polar, because both elements have the same electronegativity, so this would not be asymmetric addition, and therefore Markovnikov's rule wouldn't apply. So the next thing to state is, what is Markovnikov's rule? So Markovnikov's rule, I'll just give the simple textbook definition. Markovnikov, apologies if I spell his name incorrectly. Markovnikov's rule simply states that the carbon rich in hydrogen get richer, so the rich get richer. So simply translated, we're talking about rich in terms of hydrogen content. So the best way to explain this is to look at a specific example. And what I'm going to introduce now is a 3-carbon compound that we're going to try and maintain or study its fate as we go through various organic syntheses using the same compound. So if I introduce propanene to you, so if I draw a propanene right here, so CH3, this is the example we're going to look at now for asymmetric addition. So asymmetric addition of propanene. We're going to use water as an example for the asymmetric molecule. And when we're trying to talk about Markovnikov, when you're trying to identify which carbon is the most rich in terms of hydrogen content, I find it easier if I get students to take the condensed formula and turn it into a structural formula, because you can also identify where the hydrogen adds on and where the oxygen adds on, or the OH adds on. So if we open this condensed formula out, this is what we're actually looking at. We're looking at the addition of water, and if we open the water molecule out as well, remember up the top I said water is going to split along this line here. So it's going to be addition of OH onto one of the carbons, and then this hydrogen gets added to the carbon which is most hydrogen rich. So we need to identify which carbon is most hydrogen rich. Now with an alkene, addition on an alkene, we're focusing on the carbon-carbon double bond, or the carbons involved in the double bond, because that's the functional group of an alkene. So we can only look at both of these carbons and try and decide which one is hydrogen rich. So it's pretty obvious, hopefully, that this is the richest. Okay, so as a result, this hydrogen is going to be added on here, and then the rest of the water molecule is going to go to the poorer carbon. So if we're going to have to get a new page now to just draw the product, but you have a major and minor product, and we're going to look at those now. So if I get a new page, so the major product from this addition, I'll just draw it the reaction that we were looking at again. So propanene, we've determined that's the richest carbon, and we're adding H2O where there's asymmetric split of that molecule. So the major product is going to be a secondary alcohol. Now I'm going to use some colors just to help with the coding here. So the OH group, we're going to keep that green. So we'll stick that on here. And then the hydrogen, I'll just highlight that with some orange. So maybe a bad color since everything's in orange. Let's use this color here. Okay, so that extra hydrogen gets added on. We'll stick it on the end of the molecule here and complete it. So carbon bonded to carbon, and that is your major product. So this is your major product, and this is a secondary alcohol. Now with any addition reaction, asymmetric addition reaction, you can get major and minor product. So we draw the minor product in, and the minor product simply involves that this hydrogen is added to the carbon which was poor instead, in which case you have this situation. Your hydrogen will be here, additional hydrogen will be there, and your OH group will be here instead, in which case you're forming a primary alcohol. So this is where the question of purity of organic synthesis comes into play, because if you want to just make a secondary alcohol, but you have the primary alcohol forming as a byproduct of the process, then you need to have some ways of determining the presence of the primary alcohol. So this links us in nicely to elimination reactions now. So we're going to take a look at elimination, and we're going to focus on the elimination of our primary alcohol. In this case, we're going to take this primary alcohol, which is propan-1-ol. So we're going to take propan-1-ol, and we're going to eliminate the OH group from it and try and return it to its parent alkene, which was prop-1-ene. Okay, so elimination reactions is the second type of reaction we want to take a look at. Elimination. Okay, so an elimination reaction, by definition, atoms are removed from a molecule. Atoms are removed from a molecule, and a double bond forms. Okay, so with elimination reactions, you're always going to form a double bond at the end of it, and this will result in alkenes being formed, essentially. Or a carbon. So with elimination reactions, if we go back to our level 2 flowchart for a second, the one that we had highlighted, which was this one. So we're into step 2 now. We've done step 1, addition reaction on an alkene. We formed an alcohol. We formed a primary and secondary as major and minor products. Now we're looking at an elimination of a primary alcohol back to an alkene. So with the definition we just said, an elimination reaction, atoms are removed from a molecule and a double bond forms, aka an alkene. So if we take our primary alcohol propan-1-ol and take a look at elimination on it, just to keep some consistency in the discussion. So we had our hydrogen had been added on there. This was the minor product. So that's propan 1-ol. Now, with elimination, we're trying to eliminate water, essentially. So we're trying to reverse the process. We're trying to eliminate the water. So what we use is concentrated sulfuric acid. So a concentrated acid has little or no water in it, and therefore is a highly dehydrating agent, highly dehydrating. And the rule which comes into play here now is Zaitsev's rule, or Zaitsev's rule. Spell that correctly. Zaitsev's rule. Also referred to by some teachers as the anti-Markovnikov rule, because it's the opposite. In this case, the poor, in terms of hydrogen content, get poorer, poor get poorer. And in order to identify the carbon which is poor in hydrogen content, in this case, you're not looking at the central carbon, as I like to call it. So the central carbon has the hydroxy or the alcohol group attached to it, so that you don't touch that when you're removing hydrogens, in which case you're looking at either of these two carbons here, and the carbon which is poorest in hydrogen content is this one. So this is the poorest carbon. So as a result, we're going to eliminate this hydrogen, which is the one we put there in the first place. So eliminate this one with the OH group. And as a result, your product is going to be returning to an alkene. So you're going to have a double bond forming here. You've removed the hydrogen from that central carbon, and you've also removed the OH group from the end here. So you have water as a byproduct of this reaction, which was your eliminated. So that's back to your prop-1-ene. So that's elimination is the direct opposite to addition of water in that case. You can also have elimination of a halogen from a haloalkane to form an alcohol. Let's take a look at the flowchart for a second, make sure I'm saying the right thing here. So elimination of a haloalkane, to form an alkene. You typically substitute in the haloalkane to form an alcohol. So that's another example of elimination. There are a few others when you come into this other section here of the level 3 flowchart, so you can bear those in mind. But they're the two main examples: the elimination of water from an alcohol to form an alkene, and the elimination of a halogen from a haloalkane to form an alkene also. So that's elimination. Now let's take a look at the third type of reaction, which we said was going to be nucleophilic substitution. Nucleophilic substitution. Okay, so substitution reaction, by definition, simply involves atoms in a molecule are exchanged for other atoms. Now, a nucleophile, by definition, is something, so it's a molecule, an atom, or a molecule, or an ion. So let's just call it a species with a negative center. And it's best to just look at some examples. So the typical examples we come across as good nucleophiles would be OH minus, for example, substituting an OH minus, so substituting an OH group onto a haloalkane to form an alcohol. Similarly, you could have a chloride ion for halogenation. You could have Br minus if you're adding bromine onto an alkane. All have negative centers. Water, so the OH group, water is addition. Substitution, another example would be ammonia, alcoholic. The nucleophilic center here is from the lone pair of electrons which are on your nitrogen. So in all cases, all of these species have some sort of negative center which attacks a carbon which is slightly positive within the reagent or within the organic molecule that you're trying to attack. So for nucleophilic substitution, like I said, I'm going to take a look at the chlorination of a tertiary alcohol, because this is a big focus area for level 2 and level 3. It used to be not a major focus for level 2, but it's a lot more so now. Um, so I'm taking a look at this section here now. So number 3, I'm taking a look at this section, nucleophilic substitution on a tertiary alcohol to form a haloalkane. And there's your substitution down there I just mentioned as well. You can have substitution of ammonia, which is also a nucleophile because of its lone pairs, and that can make an amine. Simple enough process. And you can also have substitution just along here, which is substitution of bromine on an alkane to form a haloalkane. So there's the major examples for substitution from the level 2 poster. All right, so chlorination of a tertiary alcohol. All right, let me see if I got a lot of space here. So I've got a new page for this because it's going to be quite big. Okay, so we're going to look at substitution reactions of tertiary alcohols. Okay, so specifically nucleophilic substitution. And the specific example I'm taking is chlorination because you're adding chlorine. Chlorination. Okay, spelled incorrectly. Let's correct that. Chlorination. Chlorination. Okay, now, with nucleophilic substitution on a tertiary alcohol, there are 1, 2, 3, 4, 5 possible sources of chlorine that you can use. So 5 possible nucleophiles. And the compound that I'm going to take a look at is going to be tertiary alcohol as follows. So with a tertiary alcohol, you must have a central carbon with the OH group attached, and you must have 3 other carbons attached to it. So the possible chlorinating agents, we can use PCl3, phosphorus trichloride. We can use PCl5, phosphorus pentachloride. We can use SOCl2, which is thionyl chloride. Or we can use a mixture of ZnCl2, zinc chloride, plus concentrated HCl, which is known as Lucas reagent. Okay, so that's 1, 2, 3, 4, 5. Is that 1, 2, 3, 4? 4 possible reagents. Can't count properly. Okay, so 4 possible reagents, which are plenty to consider when you have to look at chlorination on a tertiary alcohol. So what I'm going to do is I'm going to just take each one in its turn. So if we take our compound CH3, OH group, CH3, CH3. So plus PCl. Let's start off with SOCl2. Okay, thionyl chloride. All right, so it's a straight substitution. So the OH group is going to be substituted for a chlorine from the thionyl chloride. So what you do is you write down your product, your halogen product, which is just simply straight swap of the OH for the Cl rather. And there's one of your products. And then with SOCl2, you always get HCl as a byproduct. And then whatever's left over is going to make up SO2 gas. Now this is a great benefit from using thionyl chloride above some of the other reagents like PCl3 and PCl5, because the SO2 gas is easily separated. Since the rest of the chemicals in the equation are all aqueous, so this is aqueous, this is going to be aqueous, so SO2 byproduct is easily separated, which gives you a higher yield of haloalkane than PCl3 or PCl5, and you'll see why in a second. So we take a look at the same tertiary alcohol. That was 1 of 4, number 2. Same tertiary alcohol plus PCl3. Okay, PCl3, phosphorus trichloride. You'll still get the same chloroalkane or haloalkane product, but in this case you get phosphoric acid, so H3PO3. And just to balance this equation up, if you had 3 chlorines on this side, then you needed to have 3 of the product there and 3 of the alcohol at the start. So the problem with these products is both of these are aqueous, and this shows you that they'd be quite difficult to separate in comparison to using the thionyl chloride, SOCl2. The third chlorinating agent we could use is phosphorus pentachloride. So once you memorize these four equations, then it's just a case of repeating them and making sure that they're balanced. PCl5, phosphorus pentachloride. You get the same product as usual. Okay, same product as usual. In this case, you're going to get HCl as well. And then whatever's left over makes up POCl3. And I had to look up the name of this compound, I'll admit. This compound is known as phosphorus oxychloride, or it's also referred to as phosphoryl chloride. Okay, in any case, the equation should be balanced. There you have 3 chlorines plus that one, which transfer your 5. And then the OH group has been substituted with one of the chlorines. The fourth possible way to chlorinate your tertiary alcohol, and it has to be a tertiary alcohol for this method to be effective, is to use Lucas reagent. And Lucas reagent is a way of distinguishing between primary, secondary, or tertiary alcohol, because the rate at which Lucas reagent reacts is fastest with a tertiary alcohol, very little with a secondary alcohol, and nothing, if anything at all, with the primary alcohol. So that's something else which comes up in your assessments. But Lucas reagent is ZnCl2 dissolved in concentrated HCl. And the great thing with this reaction, if it is a tertiary alcohol that you're working with, is that you'll quite easily form your haloalkane. Same product we've been forming the whole time, but your other byproduct is water, which is quite easy to separate. And so the Lucas reagent would be useful if you had a tertiary alcohol that you were working with. So that was quite extensive, but nucleophilic substitution, as I say, is a big focus for level 2 and level 3, and that's your 4 ways to do it. So let's just take a look at our flow chart again. So we've covered now the 4 ways of chlorinating your tertiary alcohol to make a haloalkane, and that's some good discussion of substitution reactions. You can also reverse that situation and substitute a haloalkane with a hydroxide, aqueous hydroxide ions, for example. That could be from sodium hydroxide or potassium hydroxide aqueous, and that will return you to your alcohol. And it will be a primary, secondary, or tertiary alcohol, depending on whether you started with a primary, secondary, or tertiary haloalkane. So the last, number 4 we need to look at. So we're nearly there. It's a long video, but has to be covered. So redox reactions. Redox reactions we're briefly going to take a look at. Not too much to talk about here. For redox reactions, so number 4, a redox reaction, as you remember from your redox chemistry, hopefully involves reduction and oxidation of a species. Reduction and oxidation of a species. Okay, so if we take a look at primary and secondary alcohols, because that's all we need to really consider in level 2 or level 3, and you'll see why in a second. So if we take sticking to our 3 carbon alcohol, so this is propanol, propan-1-ol. So with the primary alcohol, if we use an strongly oxidizing agent like acidified permanganate, or you can use acidified dichromate. Right, in either case, both of these reactions have a nice color change. Purple for permanganate to colorless when it forms its Mn2 plus reduced species. And dichromate, which is nice and orange, forms a nice green color as it forms Cr3+, which is also its reduced species. So in either case, the oxidizing agent by definition is reduced itself, and then the terminal carbon, which is bonded to the OH group or hydroxy group, is the one which is oxidized. So initial oxidation will form the aldehyde equivalent. So it's going to look like that with the aldehyde group, so that will be propanal. And then if you further oxidize it with the same reagent, so acidified permanganate, then you'll form your carboxylic acid, which is C double bond O bonded to OH. Secondary alcohols, so for example CH3, CHOH, CH3, same thing. You'll oxidize that to a ketone, so CH3 ketone has another carbon stuck onto the central or carbonyl carbon rather than a hydrogen, which was the aldehyde case. And that's as far as they go with terms of oxidation. And a tertiary alcohol has no reaction. You cannot oxidize tertiary alcohol. So there's some tests that we'll talk about involving using Tollens reagent and Benedict's to distinguish between a primary and secondary, or to distinguish between an aldehyde and a ketone rather, and that will be discussed later when we do a video on testing for these different products. So that's as far as I'll go with oxidation. The last thing now is, because this has brought us on to looking at carboxylic acids, I'm just going to quickly look at the fifth type of reaction, which are condensation reactions. So we get one final page. So reaction type number 5, condensation. Okay, so a simple definition for a condensation reaction in organic chemistry. You have two relatively large molecules which join together with the loss of a much smaller molecule. Typically in your chemistry, you will come across the loss of water or HCl. Two good examples. So the two examples I want to take a look at, and let's quickly go back to the flow chart. Now the level 3 flow chart would illustrate this better, but if you have a carboxylic acid plus an alcohol, you will make an ester, which is a condensation reaction. If you have an acyl chloride plus an alcohol, you will also form an ester, which is a condensation reaction too, so plus alcohol. So if we just take a look at two examples, if I use the 2-carbon carboxylic acid, which is ethanoic acid, so CH3, there's your carboxylic acid group, so this is ethanoic acid. So ethanoic acid plus propan-1-ol, sticking to our 3-carbon alcohol as we've been doing the whole time. So propan-1-ol. Alright, so if we take those two compounds, you guys need to memorize that an alcohol plus a carboxylic acid will form an ester. And an ester, basically, if we orientate this propan-1-ol the other way around, so the OH group is what's involved in the reaction, that's the functional group. And what happens is you're going to lose a hydrogen from here, plus the OH from there, and you're going to form your ester linkage. And this reaction is referred to as esterification sometimes, for obvious reasons. So your ester is going to look like this. There's your O, which is left over here, and that acts as the linker to the alcohol. So I'll put that in green. And I wrote that the wrong way around. That's why it's not looking right. That's green. Okay, so it should have been CH2, CH2, CH3. So, of course, with the loss of the OH group and that hydrogen, that accounts for your water. So that's the condensation part. The water is being eliminated. The name of this ester, I've worked on this before. The carboxylic acid part always forms the OH section. So this is going to be ethanoate, and the alcohol which joined on as a side chain essentially forms the side chain name. So this is propyl ethanoate. And there's your condensation reaction, because you had two relatively large molecules joining together with the elimination or loss of a smaller molecule. So this is not to confuse with elimination reactions in alcohols, where you just have one large molecule and a small molecule being eliminated. And that's the difference in definition. So another example here would be an acyl chloride. Now acyl chlorides are unique only to level 3, so if you're level 2 right now, don't pass too much remarks to this. But an acyl chloride has this functional group. So it's a carbonyl carbon with a chlorine. So if we use the same alcohol here, So we're still using propan-1-ol, and then the exact same reaction is going to happen, except this time, instead of this oxygen leaving, it's going to act as the linker, and this hydrogen and this chlorine will stick together. So this is a product, you get the same ester, you can see that hopefully, and the same side group stuck onto that, plus HCl. So the HCl comes from there and there. So the product is still propyl ethanoate, but in this case you get HCl as your small molecule being lost. And the advantage of using an acyl chloride plus an alcohol to form an ester over using a carboxylic acid plus an alcohol is that these reactions are always very vigorous. So if this reaction will go, there'll be less energy input required. It's just that it's a bit more dangerous, and obviously HCl is toxic. This will needs to be removed as a byproduct, whereas water is easier to handle as a byproduct. So that's an extensive video now covering the 5 main types of reaction, and the only other video that I'll have to produce now to cover reaction types will be acid, acidic, and basic hydrolysis, which will be a whole separate video. So whether you're level 2 or level 3, you must be comfortable with all these different reaction types.